Greetings to all and welcome to this lecture. We are in module 3, which is two-terminal MOS structure. In lecture number 5, we will discuss about small signal capacitance. We said that the two-terminal MOS structure is a layered structure. We have a gate, an oxide and a semiconductor. This structure, which is called as MOS, is nothing but acts as a parallel plate capacitor when we connect the battery or connect the external voltage between its gate and body terminal. So, this structure acts as a parallel plate capacitor. It is more than a parallel plate capacitor because the other plate of the capacitor is replaced by a semiconductor. So, instead of having metal plate, we replaced it by semiconductor, and semiconductor does have the charges. These charges are classified as electrons, holes, immobile ions. So, in previous lectures, we have solved so many crunching equations to get a relationship between the gate body voltage, the surface potential and the channel charge. We found that these quantities are not purely independent, meaning one quantity is somehow related with the other quantity and the other is related on other. These are the learning outcomes of this lecture, which helps us to understand the small signal capacitance of two-terminal MOS structure. Let us do a quick recap of all MOS structure based equations. We started our analysis considering this is a two-terminal structure. This is an oxide, metal oxide semiconductor, and we said that we will apply a gate to body voltage between gate and body terminal. So, the first thing is we said that the potential balance equation, which is this. The potential balance equation says that around the loop the potential is balanced. It means the gate body voltage is nothing but the sum of the oxide voltage plus the surface potential plus the potential drop at these contacts, which is contact potential. We also saw the charge balance equation. We said that the overall charge is conserved in the system, which is Qg dash plus Q naught dash plus Qc dash is equals to 0. Here Qg dash is the gate charge, Q naught dash is an oxide charge, Qc dash is the channel charge. We are representing all this charge per unit area, and hence we introduced a new notation, a dash. Then we said that the gate charge and the oxide potential is related by this. So, ultimately you can simply rewrite as Qg dash divided by the oxide potential will give you the oxide capacitance. Further, we said that when you apply a VGB in various conditions, whether VGB is equals to flat band voltage, when VGB is less than flat band voltage, and when VGB is greater than flat band voltage, then what will happen? So, we considered then when VGB is equals to flat band voltage, at that moment there is no charge present into the channel, and hence we said that Qc dash is equals to 0 and the surface potential is equals to 0. Then we said that what will happen if you apply a voltage which is negative. If you apply a negative voltage here, it will supply a negative charge at the gate. This negative charge, because of this capacitive action, it causes a positive charge here. So, if we consider a p-type body, then the holes will accumulate near the surface, and we said that this is accumulation region of operation. In that accumulation region of operation, we have surface potential negative and the channel charge is given as positive, which is predominantly given by holes. Then we said what will happen if we tune the VGB towards the positive value. If we tune the VGB towards the positive value, the surface potential becomes positive, and when surface potential reaches to value of phi f, then the semiconductor surface charge is exactly equals to Ni, and hence it's like that you applied the positive voltage, the holes will get repelled back towards the body, and hence there is uncovered immobile ions will come into picture. That immobile ions or that region of operation is called depletion. In the depletion, my surface potential is positive, but it is less than phi f, whereas the channel charge is negative, which is given by uncovered immobile ions. Then we said that when the surface potential is further increases because of increasing VGB, your inversion electrons or the electrons from the body will come near the surface and causes inversion. This happens when surface potential is equals to 2 phi f. Further, we classified that inversion can be subdivided into three regions. One is weak inversion, one is moderate inversion, and one is strong inversion, based on the relation between psi s and VGB or Qi dash and VGB, where Qi dash is inversion charge. After solving all these equations, we came across in some fruitful outcome which relates the channel charge with respect to surface potential or the surface potential with respect to applied gate to body voltage. If the surface potential is positive, we are in depletion, the channel charge is negative, so we are in fourth quadrant, and this channel charge is given by immobile ions. Now, when the surface potential is further increases by increasing VGB value, then we are in inversion. Still, in this region of operation, the charge is governed by immobile ions, and hence this region of operation is classified or named as weak inversion. After the point 2 phi f, the charge and the surface potential are exponentially related, and hence there is a steep rise in the charge. This charge is actually governed by the electrons which are coming from the body. Similarly, in accumulation region, this is the whole contribution which is given by surface potential of negative value, and Qc dash is positive because of holes. After solving all these crunching equations, we derived finally the relation between VGB and surface potential by replacing the closed form equation of Qc dash as a function of surface potential. By solving this equation, we plotted this graph and we related that graph with the graph plotted between the overall charge in the system with respect to psi s. We said that if you increase VGB, you are actually increasing the voltage, which is surface potential. At point phi f, there is a depletion. Corresponding to that value, we termed it as VLO. We derived VLO, VMO and VHO by using a simple potential balance equation by VLO can be given as V flat band voltage plus surface potential plus gamma times of surface potential, where for VLO specifically this surface potential is given by phi f. So, this can be replaced by phi f. In a similar way, we can find out VMO, where VMO can be given by when surface potential will be equal to 2 phi f. And to calculate the VHO, means the onset of strong inversion, we need to take the higher value of surface potential, which we defined as 2 phi f plus phi z0, which is nothing but replaced as phi naught. Then what we saw, that when you increase the VGB, the surface potential increases, but after a certain point it gets pinned. So, if you see the relationship between the surface potential and the charge, till this point, till 2 phi f point, what is happening? Surface potential is linearly increasing, but the charge is not increasing. It means the change in the charge is only given by the immobile ions, and hence you need to apply more voltage to get significant change in the charge, which is this. But when you reach the inversion or just beyond 2 phi f value, this change in charge is exponential related with psi s. So if you change a small bit of surface potential corresponding to change in VGB, then there is a significant change in the charge, and hence the bottom layer of the oxide just near the semiconductor oxide interface, you will get a plenty of charge. So it will be like inversion charges forms a sheet, right? So by solving these equations, we just got that my MOS structure does have the charges at various conditions of gate to body voltage. Now what will happen if I change this gate to body voltage by a small amount? Let us say I am changing incremental, meaning if you change the voltage incremental, then there will be a change in the charge. So this change in voltage reflects the change in charge, gives you the capacitance. That is called small signal capacitance. So let us start a small signal capacitance of a MOS structure. So let me redraw a MOS structure like this. You have a metal plate, an oxide layer, and a semiconductor, and you are applying a voltage between gate to body terminal. This is VGB. You are changing the amount, you are changing this VGB by a smaller amount of delta VGB. This change in gate to body voltage causes a change in the gate charge. For example, if you are increasing VGB by a small amount, then and towards positive, then a positive charge at the gate side will increase. So to make the system neutral, the same positive charge should leave from the bottom plate of this capacitor, or the same and net amount of charge will come from the body towards the surface with opposite sign, right? It's like that. You have a parallel plate, you are applying a voltage from the top surface like this. So I am connecting a voltage like this. So the positive voltage will give much more positive charge on the top plate. So to make the system neutral, same amount of charge should leave the bottom plate, or the opposite sign of the charge will come at the bottom plate. This forms the capacitor, right? So what we'll do, if we change the voltage VGB, then it is changing the charge at the metal plate, and hence that change in charge per change in gate voltage can be defined as small signal capacitance between gate to body, and that capacitance is defined as per unit area. So we are writing CGB dash is equals to delta QG dash divided by delta VGB, correct? We know from our potential balance equation and charge balance equation that if there is a change in gate charge, that change can be reflected by negative change of channel charge, meaning we saw that the charge balance equation can be written as QG dash plus QC dash plus Q naught dash is equals to 0. If you note the change, that delta QG dash plus delta QC dash is equals to 0, because this is constant and dependent on particular fabrication. So delta QG dash can be replaced as minus of delta QC dash. Similarly, if we rewrite the potential balance equation, which can be given as VGB is equals to phi ms plus psi s plus psi ox. So change in gate to body voltage can reflect in change in surface potential plus change in oxide potential, correct? So let's solve these two equations and find out what is the equivalent capacitance between gate and body terminal. So I can do like this, I can differentiate this function by delta QG or divide by delta QG dash. this quantity will give me what? 1 over C. So you can see like that, this quantity will give you 1 over CGB dash is equals to delta psi s by d psi x can be written as d psi s by d qg dash plus d psi ox by d qg dash. Again, this quantity is nothing but the oxide capacitance or 1 over the oxide capacitance. So we can simply rewrite as 1 over CGB dash is equals to 1 over COX dash plus delta psi divided by delta QG dash. Now here QG dash can be replaced as minus QC dash. So let's discuss about this quantity, delta psi s divided by delta QG dash is equals to delta psi s divided by minus of dqc dash. What is this quantity? Again, this can be given as channel capacitance, or you can say the capacitance due to the channel charge, but with the negative sign, delta qc dash divided by delta psi s. Here you should understand the capacitance value is not negative here. The capacitance is positive. To make the capacitance positive, we are actually adding this negative term. To understand this, let us take an analogy. You have a water tank which is sealed at this side, and this is water tank. This is the inlet of the water tank, and this inlet of water is associated with a pump. What we'll do, we will connect a rubber membrane here between point A and B. This is like a membrane, elastic membrane connected between A and B. Now what will happen if you start the pump and the inlet of water allows to go in, or the water allows to go in? Then this rubber membrane will be deflected like this, correct? It means this deflection, the change in the volume of the water at the right hand side of that tank is increased, but which is opposite to the flow of the water. It's same like you have a capacitor, you applied a voltage across a capacitor. The change in this voltage delta V causes the change in the negative charge of this plate. So you can simply write the capacitance is nothing but minus of delta Q divided by delta V. So this analogy helps us to rewrite this equation in terms of delta QC divided by delta psi s. You can think like this also. If you are changing VGB, the gate charge is increases. The increase in gate charge causes a negative charge which is coming from the body to increase, and hence delta QC divided by delta psi s with a negative sign will give you the capacitance. So to formulate all this, we will see that 1 over CGB dash is equals to 1 over COX dash plus 1 over CC dash, where CC dash is nothing but capacitance due to the channel charge. You can see this picture again and try to understand that when you are connecting a voltage between gate and body terminal, you are actually giving a positive charge into the gate metal. This positive charge causes a negative ions or negative charge into the semiconductor. First, when VGB is smaller than phi f value, then depletion occurs, and after phi f and below 2 phi f, there is a depletion charge and it attracts some amount of electrons into the surface. So the overall charge was given by the immobile ions and the inversion charge, right? But when you increase the VGB beyond 2 phi f value, much more amount of inversion charge or the electrons will come from the body and actually form a layer of negative charge here like this. So this is again considered as a parallel plate capacitor, where this dielectric is replaced by silicon dioxide or effective oxide thickness with some other designed with some other material. So, from here you can see that we have two capacitance, one is oxide capacitance COX and one is channel capacitance CC dash are connected in series. So, you have this as a gate terminal, this as a body terminal, and you have a voltage connected between gate to body. This is VGB. The voltage between this and this terminal is Psiox, and the voltage between this and B terminal is Psi S. Again, if you consider this region from here to here, this is considered as a neutral region. So, whatever be the voltage between this and this measured, this voltage at the body is considered to be 0. We have applied the boundary condition. So, the voltage between CC dash is nothing but Psi S, right. Therefore, we can say that the small signal capacitance of two terminal MOS structure can be given by the channel capacitance and oxide capacitance are in series. Let us do some mathematics and calculate what is channel capacitance. As we have said that the channel capacitance is nothing but minus of differentiation of channel charge with respect to surface potential. Now, we know that the equation for channel charge from our basic general analysis lecture, we said that QC dash is equals to minus of signum psi s square root of 2q Na into epsilon s into phi t e to the power minus psi s by phi t minus phi t plus psi s plus e to the power of minus 2 phi f by phi t into e to the power of psi s by phi t into phi t minus psi s minus phi t. This was the channel charge including the contribution of holes, the immobile ions or in general acceptor ions and the electron contribution. Let us do the differentiation of this and try to calculate what is the value of CC dash. So, this minus and this minus gets plus and you will get signum of psi s square root of 2q Na into epsilon s. Now, we need to differentiate this with respect to psi s. So, again it can be phi t e to the power of minus psi s by phi t minus phi t plus psi s plus e to the power of minus 2 phi f by phi t e to the power of psi s by phi t minus psi s minus phi t, right. If we do the differentiation, we will get signum of psi s square root of 2 into q into Na into epsilon s. The differentiation of square root of x is what, right. So, we will use this as 1 over 2 times of phi t e to the power of minus psi s by phi t minus phi t plus psi s plus e to the power of minus 2 phi f by phi t into phi t e to the power of psi s by phi t minus psi s minus phi t. This will all come in square root. Now, you need to differentiate this quantity as phi t e to the power of minus psi s by phi t into minus 1 over phi t. Then this will become 0 plus 1 plus e to the power of minus 2 phi f by phi t into phi t e to the power of psi s by phi t into 1 over phi t minus 1. Correct? So this is a closed form equation of Cc dash, which gives as signum of psi s by into square root of 2 into q into Na into epsilon s into this, only the numerator I am rearranging, denominator will be same, right? The numerator you can simply phi t and phi t get cancelled, here phi t and phi t get cancelled, ultimately you will get 1 minus e to the power of minus psi s by phi t plus e to the power of minus 2 phi f by phi t into e to the power of psi s by phi t minus 1. So this is the channel capacitance with respect to psi s. Now let me rewrite the denominator also, which will help us to understand the other aspect of this equation. 2 times of phi t e to the power of minus psi s by phi t minus phi t plus psi s plus e to the power of minus 2 phi f by phi t into phi t e to the power of psi s by phi t minus psi s minus phi t. Now, is the equation correct for all values of psi s? If you closely see, if I put the value of psi s is equals to 0, then the numerator, this quantity, so let me change the color of my pen with this, numerator will give you what? 1, because e to the power 0 is 1. Then you in numerator you will get 1 minus 1 plus e to the power of minus 2 phi f by phi t into, again this is what? 1 minus 1. So in the numerator you are getting 0. What about the denominator? In denominator, if you see, if you put psi s is equals to 0, you will get phi t minus phi t, then psi s is 0, so plus 0 gone, then plus e to the power of minus 2 phi f by phi t into, again here if you put psi s is equals to 0, you will get what? Phi t, psi s is 0, so phi t minus phi t. So you ended up with a 0 by 0 form. So you cannot use this equation for psi s is equals to 0. So this equation holds good for psi s is not equal to 0, right? Here the final expression is written, which says that psi s is not equal to 0. But what will happen if psi s is equals to 0? So if we ended up with some problem like limit x tends to a f x by g x in the form of 0 by 0 or infinity by infinity, we use L'Hopital's rule, which says that this can be solved as limit x tends to a f dash x by g dash x, where f dash x and g dash x are the derivative of the given function f x and g x. So we will apply the L'Hopital's rule here and try to find out the Cc dash for psi s is equals to 0. So we can simply rewrite, so this is the same equation what we derived in the previous slide. I am using the same equation as signum psi s square root of 2 into q into Na into epsilon s. Now you need to differentiate the numerator. So differentiation of the numerator will give you what? This is 0, this is minus e to the power of minus psi s by phi t into minus 1 over phi t plus e to the power of minus 2 phi f by phi t into, this will give you e to the power of psi s by phi t into 1 over phi t. Correct? Now you need to put the limit psi s is equals to 0 in the numerator, and the denominator can be given as 2 times of, again this can be written as 2 and this complete function. So let me rewrite this function as f of psi s. So this will f of psi s. and in the numerator again it will come as 1 minus e to the power of minus psi s by phi t plus e to the power of minus 2 phi f by phi t into e to the power of psi s by phi t minus 1. Now, if you see and put the limit psi s is equals to 0. If you see carefully, the lower one or the denominator is nothing but can be rewrite from this equation as C c dash divided by signum of psi s into square root of 2 into q into Na into epsilon s into 2. So, this denominator can be replaced by this quantity by using this equation. So, and you need to put psi s is equals to 0 in the numerator. So, ultimately you will get with C c dash is equals to signum of psi s square root of 2 into q into Na into epsilon s. If you put limit psi s is equals to 0, this become what? 1. So, ultimately 1 over phi t plus e to the power of minus 2 phi f over phi t into 1 by phi t divided by, you can replace by 2 c c dash divided by signum of psi s square root of 2 into q into Na into epsilon s. Again, if the signum will go in the numerator and you will get signum square. Similarly, you will get 2 into q into Na into epsilon s, because the square root of 2 into q into Na into epsilon square is this value. This is nothing but 1 plus e to the power of minus 2 phi f by phi t divided by phi t, and you left with 2 in the numerator, and this becomes C c dash square, correct. What is the value of signum square? Signum of psi s square. This is 1, right, because we know the signum function is nothing but it will give you plus 1 or minus 1, it will give you plus 1 if x is greater than 0, it will give you minus 1 if x is less than 0, but if you take square, ultimately it will give you what? Plus 1. So, signum square becomes plus 1, this 2 and this 2 get cancelled, and ultimately you will end up with this relation. C c dash is nothing but square root of q into epsilon s into Na into 1 plus e to the power of minus 2 phi f by phi t over phi t. This holds good for surface potential is equals to 0. This raises one question: does the channel capacitance exist in the flat band condition? The answer is yes, because in flat band condition, though we do not have charges, or what we said is in the flat band condition the QC dash is 0, but at any point if charge is 0 does not mean the change in charge is 0, and the small signal capacitance means the change in charge with respect to the change in voltage. So, we are actually measuring the small signal capacitance which does exist in the flat band condition. That is what it shows, because psi s is 0, meaning we are in flat band. So, in the flat band condition what happens is we do have charge carriers, right, in the semiconductor. The moment you apply a small perturbation, this charge carrier will respond immediately, and hence the small signal capacitance will come into picture even in the flat band condition. So, let me summarize. We have seen that the MOS capacitor can be formed by a layered structure which is metal oxide semiconductor structure. The small signal capacitance can be given by the change in the gate to body voltage with respect to change in gate charge. In general, what we found that the equivalent gate to body voltage, in general what we found that Gate to body capacitance is nothing but the series combination of oxide capacitance and the channel capacitance. So if you have a metal oxide semiconductor structure and you are applying a VGB, then the overall 1 over CGB is nothing but 1 over COX dash plus 1 over CC dash, where COX dash is an oxide capacitance per unit area and CC dash is a channel capacitance per unit area. So we will stop here for today. Until then, take care.